Good morning to all. Today we are going to discuss about swing equation. So it belongs to your unit number 5 stability analysis. One of the most important university question. So we have 29 equations. So based on the rotor dynamics, we are going to develop the swing equation. How the rotor is able to swing both reverse direction as well as positive forward direction, or otherwise we can say how the rotor accelerate or decelerate. So based on your mechanical kinematics, I am going to develop the equation in electrical also, both mechanical terms as well as electrical terms involved in this equation. So we have to concentrate both. So it is the electromechanical criteria only. So this is the question pattern we have. Derive the swing equation of synchronous generator connected to infinite bus from the rotor dynamics, and they extend the derivation for two parallel connected coherent and incoherent machines. So this is the question pattern we have. There are so many question patterns for this equation we have. Just one pattern I will represent it here. So introduction. So I am starting from the beginning because of the students, those who attended in the not attended in the Friday session. So only I am repeating. So consider a single synchronous machine connected to infinite bus. So it is a single machine system, single machine connected with your infinite bus bar. That is first one. Equivalent to two machine system. So I am treating the system as two machine system. So a practical power system has number of machines running in synchronisms. So we are going to deal with theoretical case only. Practical, there are so many components are connected in synchronism. So next one, I just represented the theoretical analysis. The multi-machine system can be converted into an equivalent single machine system connected to infinite bus. So theoretical, it is tedious to connect a number of buses more. So I just consider a single bus system. So assumptions, the following assumptions has to be done in your swing equation. So what is the assumption is the DC offset currents and the harmonic components are neglected. The currents and voltages are should have fundamental component alone. So DC component current, DC offset current in the sense it is a irregular current pattern evolved in your short circuit analysis. So it is not insymmetrical, it is asymmetrical. So that currents should be neglected, and the harmonic components are neglected. So we doesn't consider any first order, second order, third order harmonics here. And the voltage and the current should be your fundamental. So first cycle we are going to consider. In second assumption, symmetrical currents are used for the representation of unbalanced faults. So we are trying to evaluate only the unbalanced faults. And one more assumption is it is assumed that the machine speed variations will not affect the generated voltages. So whatever it may be the machine speed, the voltage profile doesn't affect it. So either it should be your 100 RPM, 200 RPM, 300 RPM, or more than 1500 RPM. Because of the machine speed, the voltage profile is not get affected. So that is the main assumption. And these are all the terminologies involved in the same equation. We have EKE, kinetic energy of the rotor, units is displayed. And J is moment of inertia. Omega is synchronous angular, so omega S means mechanical, Omega S means electrical. It is a small p. Here it is denoted as capital P, but actually it is small p. So small p denotes your number of poles in synchronous motion, and capital M denotes your moment of inertia of the rotor, megajoules per electrical radians or megajoules per mechanical radians. And S is power rating of the machine in MVA. H is inertia constant in megajoule per MVA or megawatt seconds per MVA. Small f is frequency per cycles or cycles per second or hertz. Del M, angular displacement of rotor with respect to synchronous rotating reference frame in mechanical gradient. And mere del is angular displacement with respect to synchronous rotating reference. Theta M, theta. So theta M stands for mechanical radiance, angular displacement of the rotor with respect to stationary axis, and theta is angular to stationary axis and electrical radiance. TMS, mechanical torque at the shaft of rotor in Newton meter. It is separate from your prime mover. And T is net electromagnetic torque. It is also Newton meter. TA is accelerating torque. TMS, mechanical power input in per unit. And last one is electrical power output, P. Yes, PE. PMS, mechanical power input in per unit. And PE is electrical power output in per unit. So these are all the terms which involved in your swing equation. So note here the mechanical losses in the rotating system and electrical losses in the stator of synchronous machine are neglected. So this is important to note, which you have to consider in your swing equation derivation. So these are all the basic things, introduction and assumptions. The terminologies are the basic things required to solve your equation. Now I move on to the derivation from the basis of your rotor kinematics. Kinematics are dynamics of synchronous motion. So first I have to get my kinetic energy. The kinetic energy in megajoule of the rotor of a synchronous machine is given by equation number 1. So this is my general equation. EKE equal to 1 by 2 times j omega sm square into 10 power minus 6. You know that j is moment of inertia, omega sm is your mechanical speed, into 10 power minus 6. So I'm naming the equation as 1. So the mechanical and the electrical angular speeds are related to number of poles in the synchronous machine as shown in the equation 2. So I have to incorporate my electrical angular speed as well as the mechanical angular speed in terms of poles I am going to write. So first one is electrical. So omega s, synchronous speed in electricals, which is equal to P by 2 times of mechanical. Or otherwise, mechanical speed omega sm equal to 2 by P times of omega s electrical. So both possibilities we can achieve. Either we can convert mechanical to electrical or electrical to mechanical, the speed in radians. So that is my equation number 2. So the two equations showing your basic dynamics of your kinetic energy. So EKE is 1 by 2 j omega sm square into 10 power minus 6. Omega s is P by 2 omega sm, and omega sm equal to 2 by P omega s. So 1 and 2 we are refining. So the basis should be continuous on substituting omega sm from equation 2 in 1. So I'm just substituting equation 2 in 1. So what happens in place of omega sm, I'm substituting 2 by P times of omega s. Already you have your omega s. So 1 by 2 j 2 by P whole square into omega s square. So 2 in 1. So 2 by p the whole square, omega s the whole square into 10 power 6. So EK equal to 1 by 2 times MWS, that is omega s, naming the equation as 3. So where M is nothing but moment of inertia, M equal to J 2 by P times whole square omega s into 10 power minus 6. So I just simplifying the entire term, that is J 2 by P whole square omega s into 10 power 6 as M, capital M. So only the EK equation is 1 by 2 times M times of omega s. So this moment of inertia is particularly used in your stability studies. So it is one of the famous equation to evaluate your moment of inertia. In stability analysis, always we have to incorporate the term M as well as H. So inertia constant term is utilized as well as moment of inertia is utilized. So wherever you have the mechanical swing, you have M as well as H. Yes, another useful constant which is popularly known as inertia constant H. It is defined as a ratio of stored kinetic energy in megajoule at synchronous speed by machine rating in MPa. Excuse me. So this is my inertia constant ratio. So the stored kinetic energy in megajoule is nothing but your EKE 1 by 2 M omega S square S. That is your EKE. By your machine rating is nothing but S. So therefore H is equal to EKE by S. Mathematically I am written here. So this is my equation number 5. So on substituting for EKE from 1 in 5, so I have to incorporate my equation 1 in 5. So the H is modified as 1 by 2 times J omega Sm square by S. So I am naming the equation as 6. So now I am going to substituting EKE from the equation 3 in 5. So 3 on the 5 substitute panamna, H is equal to 1 by 2 M omega S by S. So from the 7th equation, I can easily write what is my M. So M moment of inertia is nothing but 2Hs by omega S in eduthalam. Correct? So individually, I determined the equation for H as well as M. 2Hs by omega S. So you know that your omega S is 2 pi F. I am substituting in the M expression. So 2Hs by omega S is 2 pi F. So 2 get cancelled. Remaining terms are Hs by pi F in megajoules seconds electrical radians, equation number 9. So in equation 9, the moment of inertia M is apprehended in megajoules seconds electrical radian. Sometimes it may be megajoules electrical degrees also. By our convenience, we can convert electrical degrees or electrical radians. So in case of degrees means I have to replace pi by 180. Correct. எனக்கு வந்து டிகிரியா வேணும் அப்படின்னா பைக்கு பதிலாக 180 சப்ஸ்டியூட் பண்ணா போதும். In 9th equation. Yes, I am substituted here. M is equal to Hs by 180 F in megajoule seconds electrical radians. So now I have to get my per unit value of the M. What is your per unit value definition? Actual quantity by base quantity. What is my actual quantity for the moment of inertia? SH by pi F or Hs by pi F. My base is base MVA. So here I am considering my base MVA as SB. MVA அப்படின்னு போடுவோம் இல்லையா, அதாவது MVA பதிலாக S யூஸ் பண்ணிருக்கேன். So SH by 180 F by SB in degrees. So this is my 11th equation. So if the machine rating S is chosen as base value, then S equal to SB. In case of 11 and 12 can be rewritten as. So H by pi F or H by 180 F. So So this is the actual per unit value of the moment of inertia with your machine rating base MVA, M per unit. So these are all the basic dynamics involved in your swing equation. So number equation the fundamental things needed to derive your swing equation, the 12 equations. So this is my actual swing equation. In university question, 2 patterns the question is asked. The first pattern is from the rotor dynamics obtain the swing equation, and second pattern is derive the expression for swing equation. So if they are asking the second type, that is derive the expression for swing equation, means you have to start from here. Suppose the question should be from the rotor dynamics, you have to derive the expression in the swing equation, means you have to write all the bases. So I am having the two machines, so generator as well as motor. So consider the speed. Omega sm anti-clockwise. For generator as well as motor, the speed is anti-clockwise only. Here the electrical torque and mechanical torque both are reverse, that is opposing. Same direction of in generator, the electrical should be clockwise, mechanical should be anti-clockwise. Similarly, in motor, mechanical should be clockwise and electrical should be anti-clockwise. So this is the torque acting on the rotor of synchronous machine in the swing equation. So this is the general considerations for swing equation. Designers நார்மலா எடுத்துக்கிறது அவங்களா கொடுத்தது. ஏன் சார் இது நம்ம கிளாக் வைஸ் மாத்தி கூடாது, ஆன்டி கிளாக் வைஸ் மாத்தி கூடாது கேட்டீங்கன்னா அப்படிலாம் பண்ண முடியாது. இட் இஸ் ஃபிக்ஸட். சரியா? அவங்க தியரட்டிக்கல் அனாலிசிஸ்க்காக சயின்டிஸ்ட் வருது. So the basis for the diagram, the rotor of the synchronous machine is subjected to two torques. So one is electrical torque, another one is mechanical torque, TE and TM, which are acting in opposite direction as shown. So in the diagram itself, I mentioned the opposite directions. So the notations, T is net electrical or electromechanical torque in Newton meter. TM is mechanical or shaft torque supplied by the prime mover in Newton meter. So under steady state operating condition, the mechanical torque as well as electrical torque are equal and the machine runs at constant speed, which is called as synchronous speed. So when your mechanical element and electrical element get balanced, that is the condition for synchronous. So if I am assuming it is equal under steady state operating conditions, the mechanical torque and electrical torque is equal, it is able to achieve or able to rotate in synchronous speed. So if there is a difference between two torques, then the rotor will have accelerating and decelerating torque. So I have the term TA here, new term TA. So accelerating torque as well as the decelerating torque. So for motoring operation and generating operation, we have the reverse of the symbols. That's TA equal to TM minus TE. So TM TE positive means it is for generators, and TM TE for negative means it is motors. And theta m is angular displacement of rotor with respect to your stationary reference axis, and del m is angular displacement of rotor with respect to rotating axis. Equal to Tm minus E. So now I am going to incorporate Newton's second law of motion. We can say the accelerating torque TA is directly proportional to your angular acceleration, and the constant of proportionality, moment of inertia, J. So TA is directly proportional to your d square theta m by dt square. So in order to replace the proportionality is replaced with your J symbol. So TA equal to J d square theta m by dt square. I'm naming the equation as 14. So once you applied the Newton's second law of motion, so the accelerating torque should be J times d square theta m by dt square. So now I am substituting TA from equation 14 in 13. So in place of TA, I am substituting J d square theta m by dt square, which is equal to TA minus TE. The equation should be 15. Next one is my angular displacement theta m. So and del m is related to your synchronous speed. So if I am incorporating the two terms in a single equation, theta m equal to omega smt plus del m. So this is my equation 16. This is general equation for your angular displacement in place of your mechanical speed with respect to time and your angular motion, that is mechanical angle del m. So this is 16. So next step, I have to differentiate with respect to t once time. So d theta m by dt is equal to omega sm plus d del m by dt, equation number 17. So in the next step, one more time I have to differentiate. So if I am differentiating one more time, the 17 should be modified as d square theta m by dt square, d square del m by dt square, equation number 18. So from the equation 17, we can say the rotor angular velocity d theta m is constant and is equal to omega sm only. So if d del m by dt is 0, so d del m by dt represents in the derivation, and the rotor speed is from the synchronous. So from the equation 15 and 18, or just comparing the equation 15 and 18, I can say j d square theta m by dt square equal to tm minus t as d j d square del m by dt square. So both are equal only. In the statement we are proven, so del m theta m is equal only. So I can modify the j d square del m dt square equal to tm minus t in the 19th expression. Theta m பதிலா del m மாத்திட்டேன். So next two terms is PM actual, PE actual. So PM is mechanical power, PE is electrical power. We know that power in mechanical is 2 pi nt by 60. In general, omega t. So omega, you know. So I can write for mechanical separately and electrical separately. PM actual equal to omega sm PM. From this TM is PM actual by omega sm. Equation number 20. And PE actual equal to omega sm into T. From this T is PE actual by omega sm. Equation number 21. So on substituting Tm and Te from equation 20 and 21 in equation number 19, that is T square del m by dt square equal to Pm actual by omega sm minus Pe actual by omega sm square. So here the term J is missing here. So now I am simplifying further J omega sm. So I am bringing the omega sm to the left hand side. Already we have J. So J omega sm d square del m by dt square equal to Pm actual minus Pe actual. So equation number 22. So now I am introducing the inertia constant again in the equation, inertia constant H, megajoules per MVA, and then power rating is in MVA. So H we know that 1 by 2 J omega sm square by S. So from this equation number 23, I can extract my J omega sm. So J omega sm is 2 Hs by omega sm, equation number 24. We know that your kinetic energy 1 by 2 J omega sm square. So the kinetic energy now Ke by S, that is your H. So from your 22 and 24, so this is your 22 J omega sm d square del m by dt square Pm actual minus Pe actual. What is your 24 J omega sm equal to 2 Hs omega sm. I am substituting that is 2 Hs omega sm d square del m by dt square equal to Pm actual minus Pe actual. So from the second equation, you know that omega is equal to P by 2 omega sm. Omega sm equal to 2 by P times of omega s. P is known as number of poles in synchronous motion. So yeah. So இங்க இருக்க பார்த்துட்டோம், உங்களுக்கு அந்த simplify பண்ண போறோம் further. So on substituting omega sm and del m from equation 26 and 25. So 2 Hs 2 omega s by P. In place of omega sm, I am substituting here next one is d square 2 del by p dt square, which is equal to pm actual minus pe electrical. So இங்க பாரு என்னென்ன terms cancel ஆயிடும்னு பாத்தீங்கன்னா இங்க வந்து 2 by p cancel ஆயிடுமா, denominatorல இருக்க 2 by p numerator இருக்க dp, so like 2 hs by omega s d square del by dt square னு வரும். So pm actual minus pe actual. So now substitute omega s equal to 2 pi f in equation number 27. So if I am substituting omega s equal to 2 pi f, I am substituting here 2 hs by 2 pi f. So 2 to get cancelled. Remaining term is hs by pi f d square del by dt square pm actual minus pe actual 28. So we know that pm actual is in terms of base value, pm is pm actual by s, and the per unit value of electrical power in actual is P is P actual by S. So I'm just dividing by your base value. So now the equation is modified as just by pi f d square del by dt square is Pm actual by S minus P actual by S. So I can say the entire equation as Pm, and here the entire equation as Pe. So this 29th expression is called as swing equation. So it is a fundamental equation that governs your dynamics of the synchronous machine rotor. So you get the pattern of second order differential equation. So from your basic rotor dynamics, we may obtain the swing equation. So based on the swing equation, we have the application for your stability series. So one application is equal area criterion, and second application is determination of critical clearing angle in time. So the two applications we are going to extract from your swing equation. So this is the fundamental equation for the two applications of your stability analysis. In the forthcoming classes, we are going to discuss the two. Do you have any doubts or clarification in the 29 expressions? The 29 expression ஏதாவது டவுட் இருந்தா எந்த ஸ்டெப்ல டவுட் இருந்தாலும் கேட்கலாம்ப்பா. I'll attach PPT for your reference. In the PPT and attach பண்றேன். Doubt இருந்தா கேட்குங்க. So we have 15 more minutes more. Attach the PPT. If you have doubt, means you may ask.